Hi, friends. Welcome again to another episode of Beyond the Clouds, Edge to Edge Transformation. This transformation is literally global. It's a joy for me to talk to people who have lived and worked in not only different parts of the world, but in different ways in the hardware, software, stack, and in various ways from the connectivity to the core chips and the design automation part and the IP part. And one of the amazing people I got to know is Axel Kloth. Axel, tell us about your journey. How did you become the Axel that we know today?
Thanks for having me. It's a great honor to be on your show. My name is Axel Kloth. I'm the CEO and founder of a company named Abacus Semiconductor. I first want to explain what we do and why we do that, and then get to the path on how we got there. I've been using supercomputers for a very long time, since about 1989. I've always been frustrated by the fact that they don't quite do what we want them to do. And both as a user of supercomputers and as a physicist taking things apart and trying to make them better, I came to the conclusion that there are severe shortcomings in how we build supercomputers. Initially, supercomputers were based on the fastest possible CPU you can find, very expensive. There was nothing off the shelf in them. So think back to the Cray Y-MP. Most everybody remembers it as the machine with a red bench. It had 4 processors made out of gallium arsenide, clocked at 262 megahertz. That was the fastest you could get back then. 512 megabytes worth of DRAM was about everything you could reasonably squeeze into a machine of that size. One would think that we would have evolved from that and made sure that both the cost would be cut and at the same time the performance would be such that there's a linear scale out with a number of processors, of cores, of servers, whatever is involved in building a supercomputer today. And so unfortunately, the pendulum swung too far. In '89, with the Cray Y-MP, everything was custom and there was nothing off the shelf. Today, a supercomputer effectively is a collection of tens of thousands of servers, all industry standard servers, with nothing special in them at all. In fact, connected through 10 or 100 gigabit Ethernet or through InfiniBand, 40 gigabit or DDR 40, 80 gigabit. But what happened was Moore's law made the CPU and the core designers too successful. So today, a CPU core is an incredibly powerful and power-hungry device. But no matter how powerful we make a core, a large-scale problem such as precise weather forecast that goes out further than 5 days, or a very, very precise crash test simulation is still out of reach out of a single core. Today, the focus should be on making sure that those cores can work together, the same way that in a big factory, people are working together. And the better they work together, the more effective and efficient the production of the product is. Something that unfortunately has been forgotten in the design of a supercomputer. Focus, unfortunately, was only on the CPU core, not on how to interconnect them effectively and efficiently. We have tried to fix that for quite a while. We had a look at the effectiveness and efficiency of supercomputers and what the scale out is. If you have a look at a supercomputer consisting of 100,000 servers today in applications that require nearest neighbor communication, that require things like a finite element method in a large scale format, you will see that the performance you get out of 100,000 servers is about 5,000 times the performance of one server. In other words, whoever buys the supercomputer and has an application profile where the math and the application requires interprocessor communication, that company buys 100,000 servers, builds a building to house 100,000 servers, provides the power and electric energy, the cooling, the management for 100,000 servers, and gets 5,000 servers worth of performance out of it. We don't think that's a very good value proposition. Our system is different. We have developed a CPU that per core is not as powerful as what's out there today, but they're interconnected in a much more effective and efficient way. So 100,000 servers, in our case, would perform 85,000 times as fast as one. So we're about more than an order of magnitude better in the scale out than what's out there today. That is not because we're building better CPU cores. We focus on making sure the CPU cores can talk to each other in a much more effective and efficient fashion. We also integrate accelerator cores. If you look at supercomputers today, most of them are what is called accelerated. In most cases, there's a set of GPUs, general purpose graphics processing units, in a set of servers within this supercomputer. But the matter of the fact still is that the CPU cores do not effectively talk to the GPU cores. Neither of them talks effectively to memory, which is why CPUs and GPUs, particularly the GPUs in HPC and in AI today, have vast amounts of cache. And caches do one thing very well. They hide the latency of DRAM, but they also burn lots of power. Since caches don't compute, caches are very good at hiding DRAM latency. They are not good at cutting down the power consumption of the supercomputer. In fact, they contribute a vast amount of the power consumption and the heat generation that today's supercomputers experience. We focused on making sure the communication between CPU cores and accelerators and memory is vastly more efficient and effective than anything that's out in the market today. That is the basic premise of our inventions. We call that beyond von Neumann and beyond Harvard. Von Neumann is the basic architecture of a processor where there is input, there's output, and in the middle is the processor. That got modified early on because there's temporary data that needs to be stored. There's instructions that make up the application that needs to be stored in memory. So the CPU, in this case the processor, has an interface that connects the processor to memory to be able to retrieve the instructions, to retrieve data, to store data back if so required, and for temporary storage of data. That turned out to be a very big bottleneck. Therefore, the so-called Harvard architecture was invented that now separates the instruction memory from the memory that holds the data, both for temporary storage and for data input and data output. We believe that that's not enough, and as a result, we added a third port to each CPU, and that is the scale-out port that now connects the CPU with the lowest possible latency and the highest possible bandwidth to another CPU, an accelerator, or to memory. And by doing that, our scale-out is more linear and better than what is out there in traditional processors today. They were never intended to work together in numbers that exceed 100,000. And that's what we are doing. While we use RISC-V as the underlying processor instruction set architecture, we have substantially modified the processor, not the instruction set, but the processor, to facilitate a much more linear scale-out. We have also focused on making sure that there are hardware units that can transfer data, DMA, RDMA, through an IOMMU in each core. We again focused on not the performance of a single thread in a single core, but on the total scale-out, because we believe that is a better solution for applications where there are very large-scale problems with very large numbers of processors in a single supercomputer. Would our technology make a standard and standalone existing x86 server better? No, it wouldn't. That's not what our focus is. Intel and AMD have done a fantastic job in making sure that processors are available that solve the problems for usual everyday compute and file services. They do that very well. We do not improve upon that in an application where there's a single server or maybe two of them. But if there are hundreds or thousands or tens of thousands, then our advantage comes into fruition, and we provide a solution that's better than what's out there today.
Axel, I still remember the Hot Chips conference, and we know that hot chips is an oxymoron. We don't need that anymore. Same thing with supercomputers. At one time, it was all about speed, given that the workloads are changing. What kind of workloads are you really focused on?
Very good questions, and I think you hit the nail on the head. We're not focused on improving workloads that are solved today in x86 or ARM processors. That's not our focus. But if you look at the applications today where there is a big change needed, it is, in fact, the generation of models. So particularly when you look at AI, the input data sets, not only are they incredibly big, they require the processors to talk to each other in a very effective and efficient manner. In essence, it is like a big set of Markov chains where the probabilities have to be combined. That requires that the memory array is very large. Ideally, the memory array is cache coherent, meaning that if there's a change made here in one of the processor's memories, that change is reflected in another processor's memory if they have agreed to share this memory. Cache coherent memory is a requirement for effective and efficient computation of models for AI in the back end. That's not what today's processors or even the GPGPUs do well. While GPGPUs, for example, from NVIDIA, do that vastly better than a software-driven CPU, neither one does it as well as it could be done if we as an industry rethink how this approach should work. And so that's what we did, and that's why we did what we did. The basic premise is better interprocessor communication with very large-scale memories that can be assigned to a set of processors, a set of cores, and be made cache coherent across that domain. That's really what adds to the speed up of the system. It is not that we are building a better CPU core. We focus on how the system works together as a whole and not simply having a look at what the CPU core does. There's no way we can make a single CPU core fast enough to solve the large-scale problems that we have today, whether it is in traditional HPC, whether it is in the generation of models for GPT-4 or 5, whatever comes after that. Can be Llama, can be all kinds of models. They're all relying on very large data sets, more than 1 trillion parameters. So 1,000 billion parameters is what these processors and the cores have to chew through to create the model.
In the old days, it was good to have memory separate from CPU. CPU is where all the crunching was happening. But today, the movement of data is probably the most expensive operation. There's a lot of talk about in-memory and near-memory architectures. How do you address that problem? You already mentioned cache coherency. What about the memory itself and how it interacts with the CPUs and the GPGPUs?
I think you're absolutely correct. Again, the matter of the fact is that a good portion of the power consumption comes from data movement. The more we can restrict data movement, the better we're off. If we can share data and don't have to move it across large distances where it has to pass through many, many hierarchies of internal or external devices, the better we're off. Just for a comparison, moving data takes more than a traditional add. So if I take a byte and add a byte to it, one would think this is computationally intensive. It takes a lot of power. But the matter of the fact is that excluding the moves from memory to the register, the add takes less energy than moving that data across chip boundaries, and particularly if multiple hierarchies of internal and external devices are included. The more we can, in fact, reduce the number of moves and the more we can keep the data local, the better we're off. Cache coherency needs to be very effective and efficient. If the data we want to access is still valid or it has already been changed by another processor in the coherency domain, while of course determining whether something is still cache coherent is by itself an energy consuming transaction. The more effective and efficient we can make that, the better the energy efficiency of that part of compute is going to be. Again, that's one of the many things that we focused our effort on. There are multiple metrics for measuring the efficiency of a data communications device. Usually that's today expressed in picojoule per bit. We're in essence in industry-leading shape here. And we did that because we know that we cannot eliminate all data movement. There's some data movement that is still required, and that is what we have to make as effective and efficient as possible. In many, many cases, we don't even need to use software to move the data. That's what we use DMA for, RDMA and DMA, with the IOMMU that is part of our processor. The CPU doesn't have to do that in software. It instructs a device, and the device can now be told which parts of the memory contents needs to be copied from one place to another, or transferred from one place to another without the intervention of the CPU after the instructions have been issued.
Now, RISC-V has proven itself in IoT devices, embedded computing applications. There are a lot of people concerned about the use of RISC-V in large processors, the kind you're looking at. What made you choose RISC-V, and in what ways do you customize it so that you can make it amenable to large-scale applications?
Very good set of questions. If you look at where the compute occurs, where the real workloads are being processed, that's usually not necessarily in the CPU. We have accelerators for the math, particularly matrix math, tensor math, vector math, but also transforms. And they are controlled by RISC-V processor cores. But the execution of that is done in hardware in finite state machines. That is less latency, higher performance, and it consumes less energy as well. The instruction set architecture of the CPU that orchestrates that is less relevant than the efficiency and effectiveness of the finite state machines that execute the real workloads. You can compare that to an orchestra. In an orchestra, the conductor doesn't play any instrument, but the conductor tells the orchestra when to play, what to play, at which pitch, and so on. It's the instruments and the people playing the instruments that make the music, but it's orchestrated by the conductor. If you take a similar model to HPC, then you see that it's a natural progression of what the industry has done before. You take a device that is very good at being flexible to orchestrate something, then you take hardware devices with finite state machines and with the pipelines in these FSMs to execute the requirements of the workload and the application on that particular workload and data set. That's what we are doing. That's why the instruction set is a whole lot less important to us and the users than it was even 15 years ago. 15 years ago, all supercomputers were pretty much exclusively predicated on the workloads being executed in software on a CPU. It started to change as soon as NVIDIA came up with not only the GPGPU, but with a programming interface called CUDA. It's an application programming interface that allows a software engineer to determine what to do by looking at a list of predefined functions like matrix mult or eigenvectors. All of those can be selected from what is called this application programming interface. A function call is executed. The function call now goes to the accelerator. The accelerator executes it and gets the data back. So the novel step back then was supercomputers were accelerated by the use of GPGPUs as a certain type of an accelerator. Also, things were made a whole lot easier for the software designer by allowing them to invoke functions out of a library so they didn't have to write yet another matrix or yet another eigenvector function. That by itself was not only an inventive step, it also helped in the transition away from workloads being executed purely in software on CPUs towards an orchestration of the workloads through the CPU onto the accelerator. That is something that we can use even as of today because the software designers have now learned that it's oftentimes advantageous not to write yet another matrix mult, but just to invoke the function out of a library such as CUDA or OpenCL or OpenACC. These are all equivalent in what they cover. They make the life for the application programmer a lot easier. He or she doesn't have to rewrite any matrix mult. These functions are all existing in CUDA, in OpenACC, in OpenCL. And that's what made the transition towards the execution of workloads on accelerators much, much easier than anything in the past.
Indeed, we have to move to higher levels of abstraction in order to achieve what we're trying to do. So are you saying the way you're working on these supercomputers, you're going to make it easier for people to have software-driven hardware? Will the software be able to help reconfigure the hardware according to their needs? Would you be able to use it, say, for example, in these large farms or clouds for, say, hybrid cloud applications?
That's exactly what the industry should have considered 10 years ago. So part of the conundrum we're facing today is there is not a very good focus on the linear scalability of performance. We got to that point because supercomputers needed to be cheaper and cheaper, and in benchmarks, they achieved incredible performance, not in real-life applications. That is due to the fact that the success of the cloud was such that people said, if the cloud can achieve this, then a supercomputer should be able to do that too. But there's a fundamental difference. If I have a look at a data center, AWS or Google or Azure at Microsoft, a data center with 100,000 servers usually supports in excess of 1 million users on virtualized servers where there's not much data movement within and across the servers. So the data really stays within one virtual machine on the server. That's what today's processors do very well. They are multi-threaded, they are multitasking capable, they run multiple operating systems under the supervision of a hypervisor. They're very good at that. We don't improve upon that because we don't have to. Our target is different. A supercomputer has one user and one application at a time running on 100,000 servers. And the requirements there are very different. If you look at any kind of a large-scale matrix mult, you will see it's always row multiplied by the column and all that kind of stuff. And so theoretically, one should get away with n-squared steps through all of it. But because we now have to do some indexing and finding the row and the column, the amount of interprocessor communication is growing from one core in processor A to another core in processor B. We lose the linearity of the scale out. It's the same as if we're talking to each other, but not through a video conference. The amount of data we can exchange is directly related to the bandwidth we have and the latency. Now, if the latency increases because we are not allowed to talk, we have to write everything up in a letter and send it through a post office in New York, we can still determine that the amount of data we can convey and transfer in a single letter might very well be the same amount of data we can convey and transfer talking to each other. But because the latency is so high, the effective bandwidth is a lot lower. Instead of us having a conversation over 30 minutes, it would take us 3-4 days because the letter has to go to the post office in New York and come back. By forcing that, the latency has a much bigger effect on the effective bandwidth than the maximum bandwidth of the medium we are using to communicate. That poses a problem for supercomputers. Processor A needs to talk to processor B. Processor A may have to talk to accelerator XYZ. Both of them may have to share memory because the data they want to process is in that memory. If the latency is high, it doesn't really matter how big the bandwidth is, but the effective bandwidth will be very low if the latency exceeds a certain threshold. We will be forced to make a distinction in between what we want to outsource. Can we outsource something that's hundreds of instructions? Maybe. Or does it have to be a chunk of hundreds of thousands of instructions? And if that's the case, then the orchestrator has a harder and harder time finding chunks it can outsource from a CPU and software to an accelerator and hardware that would do it faster because of the fact that it would take so much time to get the data from A to B or from A to XYZ. And that's the thing we're addressing. And that's why we have invented the beyond von Neumann and beyond Harvard architecture to make sure that each of the cores can talk to each of the other cores, even if it's in an accelerator core, in a much more effective and efficient fashion. The same is true for memory, because ultimately, if I want to outsource a task, the task always comes with a set of instructions, and they can be meta instructions, high-level instructions, but it will always come with a lot of data. And the faster I can point the other processor to the data, and the other processor can now retrieve the data faster, the more performance and effective performance I get out of that system. And so that's why I'm saying the instruction set architecture of the processor that acts as the orchestrator doesn't really have a performance impact on what gets executed where and how fast. In our case, we chose RISC-V because I've worked with RISC-V for 10, 12 years now, pretty much ever since it came out. And it's an open source instruction set architecture. I can build a CPU based on it without having to pay license fees to ARM. And in case of Intel, of course, and AMD, they are not outsourcing and licensing out their instruction set at all. Because of the fact that RISC-V is an open source, I can build a processor that executes this instruction set architecture without having to pay royalties to anybody. But more importantly, I can optimize the processor, not towards the execution of the ISA. I can optimize it towards communication with other processors of like type. And that's the reason why we chose RISC-V. I can modify it, and it's still compliant to the instruction set architecture without being restricted to just work within one processor. And that was the biggest advantage to me.
You moved from Siemens. I visited Siemens multiple times. Amazing culture, very well organized. That was a different thinking altogether. Silicon Valley is the hacking culture. Have you been able to make the best of both environments as you start and develop your company?
Yes, I think in a lot of ways, and it has had an impact on how I work and how I delegate things. Because when I first joined the workforce, I worked for Siemens and I was a very happy employee. I always had ideas that I either didn't share with my bosses and managers and I just did it. That was not always a winning value proposition for me as an employee. The company benefited quite a bit. One of the things I started turned out to be an entire business unit later on. And after I left, they sold that to Tektronix for about $100 million. Siemens gave me the opportunity to go to the US and focus on the design of network processors for the then new IP, TCP IP and UDP and all that kind of stuff. The public networks group of Siemens was very much focused on the traditional carriers, meaning their preference was ATM. Even back then, it was very clear that that was not going to win the war. That's when Siemens said, why don't you go to the US, to all the crazies in Silicon Valley, see if there are any more crazies you can find and do something that would help us transition away from TDM and from telephony, even ATM, away to IP-based communication. So I left Munich and then moved to Silicon Valley and was involved in a grand total of 4 network processor designs that were all ready to go. By that point in time, we were already spun off into Infineon Technologies. Every single time management got cold feet and said, yeah, let's not do that, too much money. I learned from that experience that it's very difficult in large companies. And Siemens back then was 440,000 people. Infineon as a spin out was 27,000 people. Despite the fact that I thought I was in a startup, it wasn't exactly a small company. I decided after 2 years that I should join a real startup. And so I did. I was appointed to the technology advisory board of a startup that had built a CC NUMA type switch for the EV67 bus, which was the bus on the Athlon MP. We taped it out and we tested it. Basically came with 0 bugs in it. And we started thinking about approaching all of the system vendors, Compaq and Fujitsu. I was tasked with finding out what we could do with the technology and ultimately came up with, let's make a high-density, high-speed serial link. That turned out to be CML-type transceivers, industry first. Everybody said you can't do it, you need gallium arsenide for it. I said there's no reason for it. Yeah, we don't push the electron mobility requirements on bulk CMOS. Back then, LSI was the king of the hill with LVDS, and we taped out. And as a teeny tiny startup, we tripled the bandwidth at a third of the power consumption in a process node 1 generation older. The switch itself was repositioned and repurposed to be a communication switch, and we got 3 customers. We managed to sell those actually at a very nice profit. That gave me the first insight into how a startup could work and how much fun it can be and how successful it can be. We got acquired relatively quickly within like 10 months of me being on board for $394 million. That was a very good experience with regards to the learnings, not only technology, but also the way that a startup works, the way that it works to get from a stage of funding to a stage of sales and then to a stage of acquisition. We got stuff done that everybody said is not doable. It was a lot of fun. We got acquired, we got spun off and then spun off again. When I joined the startup, it was initially Poseidon Technology. Then it became Hot Rail after renaming. When we signed the contract to be acquired, the acquiring company was Rockwell Semiconductor. Before the ink was dry on the contract, it became SP Technologies. I changed business cards without even moving my desk 4 or 5 times in 12 months. That's the story of Silicon Valley.
Now that you're here and doing all these startups, when you were at Siemens, you were the rabble rouser, probably a lone rabble rouser. Now you're in the mecca of rabble rousers. There's practically nobody who does things by the rules, especially in startups. In what way have you changed? Are you the same, Axel? Was that solo rabble rouser, or have you changed as a person?
I try to learn as much as possible from what I've experienced. And one of the things I want to avoid is a situation in which I become the person who has the only correct opinion. I try to really not do that. My experience tells me XYZ should be done. And I tell my design engineers, hey, let's do XYZ. But I also tell them at the same time, if you think there's something that we're either not seeing or can work better, please prove me wrong. And if you prove me wrong and what you did and said works, kudos, no problem, none whatsoever. What I don't like, and I tell that to every single one of my contractors and employees, is whining about a status and not fixing it. You can criticize me, you can tell me I do things wrong, that's fine. I don't mind. Tell me what you think works better. And then we try it out. In a startup, one thing you learn is you have a plan that gets you from A to B. You might start at A. The number of detours you have to take to get to B is incredible. And sometimes you don't even want to get to B anymore once you're about halfway there. I try to be the one that says, let's take this general direction and see where this goes. And if you have an idea that is better than mine, please bring it up, prove me wrong. And so far, it has worked really well. I've had brilliant interns that did incredible work. That was only due to the fact that I said, take it and run with it. I don't care how you work. If you only work in the middle of the night or only at lunch, I don't care. But when you come on board, we agree that you do XYZ. One thing I've come to appreciate the older I get is people who are a little bit on the lazy side, but smart. They usually turn out the best because very simply, they think a lot about how to do less work. We've had it happen a bunch of times now. Repetitive work is something that frustrates everybody. If writing the Verilog is too boring, write a code generator that writes the Verilog. Right? I had an intern write a generator tool for the enter, fuse, multiply, add, and the partial sums, and optimize it with an optimizer script. The outcome is that ours, by cycle count, is by far the fastest fuse, multiply, add on the planet. So not only is it working and is correct, it already showed very fresh grads that they have the freedom to do the work any way they want. Because ultimately, why would I tell them how to work? Their parents sent them off to study, to learn. And the first thing you do at school, at university, is you learn how to learn. You don't learn the subject matter. In the first 12 months, the subject matter is irrelevant. All a university does is it forces you to learn how to learn. And once they've done that and they know how to do stuff and they know how to learn, why would I tell them how to do something? All I care about is that at the end, you've got the result, you've got the code, it is understandable by somebody else, it is testable, and it's correct. And even if there's a few minor bugs, we'll find them, fix them, no big deal. But I will never tell you how to do your work. And more importantly, when you're stuck, you will come to me. You will not be stuck for 3 days. When you're stuck for 8 hours, you come to me, you tell me where you're stuck. And even though I may exactly know what the answer is, plus all the code, I will also never give you the answer or the code because I want you to finish your project. I will ask you questions that point you towards your inventive process to find the solution yourself. And that has proven to be reasonably successful. I've got a retention of my employees and my interns that is way beyond the industry standard.
You remind me of Schumacher, who said, small is beautiful and less is more. And it's truly the case that in Silicon Valley, we try to get things done with very little and try to maximize. Having spoken of that, if there are other rabble rousers, whether it's in Germany or in Bangalore or in Taiwan, it doesn't seem that simple to start companies and make them successful in other parts of the world. Does that mean everybody has to move to Silicon Valley? Or is it possible to create the startup culture in other parts of the world?
The answer is a very clear yes and no. The distribution of smart people all over the planet is the same. You will find smart people all over the place. Most of the things that we are focusing today on require a certain threshold in the number of people who can be brought on board to implement it. Let's say there is a brilliant person somewhere on the North Pole. The likelihood that he finds another 20 people who are equally brilliant in what they need to do to implement his idea, that likelihood on the North Pole is very, very low. Here in Silicon Valley, you can take a stone and throw it any direction you want. You will find an expert in that direction. Therefore, it is much easier to put enough critical mass together to build a company and then get funding. Ultimately, the idea alone isn't good enough. You have to show that it's implementable. So the same way that I did at Hot Rail. I could have just theoretically proven that the electron mobility in bulk CMOS was good enough for CML versus LVDS. But showing it theoretically is one thing. The other thing is take that and say, hey, we now build it and we show you. And by the time we show you, we win. We can say, we've got the theoretical underlayment, we know it works, and not only do we have that, we have implemented it because we have the right people. And that critical threshold of people isn't there everywhere. You may find it around Boston. Very likely are not going to find it around Houston and Austin. Very likely there will be lots of spots in India where there are enough people to fulfill the threshold of building something, not only having the idea, but building something. In a lot of ways, Silicon Valley is unique and will hopefully stay unique and relevant, but there will be other spots, other places on the planet where there's an equally good and valid set of startups that can do what they promise they will do. If you just look at unbiased numbers, the distribution of really, really smart people is pretty much homogeneous.
I love the name Abacus because I used to play with it when I was a little kid. How did you name your company, which is making all these amazing supercomputers, high-performance computing devices, Abacus?
So the name is really clearly derived from the Greek mechanical machine that helped humans with math. Once we graduated from the 10 digits we have on our hands, we needed something to augment that. And so I thought, we're at a stage where supercompute has to be rethought, and therefore we need a new start. And so that's why I named it such that it indicates this is a new start, a new way of doing what we need to do that is, in a way, novel, but also at the same time tells people what we do is a tool. Ultimately, a supercomputer is a tool. And I think a lot of people have forgotten that. We use a tool the same way we use a hammer. The better the hammer is, the more nails we can nail in an hour. The better the supercomputer is, and the better the components are that make up the supercomputer, the bigger the problem is that we can solve. Because I can guarantee you the problems that humankind faces will only go up in complexity. It ain't going to be easier ever again. The complexity will only increase. For us to be able to solve computational problems that we derive from problems we are facing, whether physical problems or how to distribute food or how to make sure we've got enough potable water that we can distribute so that we can support 8 billion people on this planet. It's huge, large-scale logistics. Ultimately, it's our obligation to make sure that everybody has shelter, water, food, and access to education.
Indeed, Axel, we've covered so many different and interesting topics, and that's why I like talking to people who have various backgrounds and are willing to take the risk of talking about it, implementing something real rather than just talk about it. And you're one of them. It's a joy talking to Axel. To people out there, I would love to hear from you. What are the things that bother you? What are the ways in which you are mitigating risk? How are you creating value? And how do you want to see the world change in a way that makes the most sense to all of us? So please come forward. Love to hear your stories. Axel, may you accelerate the development in a way that helps people, helps the planet. Dankeschön for all the work you're doing. All the best to all the people who are working with you as well.
Great. Thank you very much. It's greatly appreciated.